In our third video on asymptotics, we're going to talk about big O and logarithms. We'll begin by remembering the definition of the logarithm. The logarithm is the inverse of the exponential function, and it is defined as such. We'll say that the log base b of n is equal to x is defined as b to the x is equal to n. Okay, so if b to the x is equal to n, well, the inverse of this exponential function is log base b of n is equal to x. Great. Some to get an appreciation for the logarithm, it's useful to remember that log base 10 of a number n is the number of digits to represent the number n. And log base 2 of n is the number of bits in the number n. Great. So we're going to be looking in this lecture on the relationship between the logarithm and asymptotic notation. And so we'll start by writing down a couple facts. So fact 4, for all constants b and c bigger than 0, the log base b of n is big O of log base c of n. Fact 5, for all constants b and x bigger than 0, log base b of n is big O of n to the x. Okay, so fact 4 is telling us that the base of the logarithm doesn't matter when we consider the asymptotics of a function. In other words, any log base b is asymptotically has the same asymptotics, is asymptotically upper bounded by log base c of n, but of course you can swap b and c, and so log base c is asymptotically upper bounded by log base b of n, and if you recall our last discussion about exact bounds, we can derive from fact 4 that log base b of n is big theta of log base c of n. These are asymptotically equivalent. Great. Fact 5 is telling us that if we compare the log to a polynomial function. So the log base b of n for some base b compared to the polynomial n to the x for some constant x. This says that the log grows asymptotically slower than, no faster than, n to the x for any x that's bigger than 0. Okay, and so, in particular, think about x equals 5. Think about x equals 0.0005. Fact 5 applies to both these two cases. Log base b of x grows asymptotically no faster than n to the 5. It also grows asymptotically no faster than n to the 0.0005, or any non-negative number x that you think of. Great. I'm going to give you the proof of fact 4. Okay, and so we're going to start out with just the definition of the logarithm, that log base b that log base c of n equals x implies that n is equal to c to the x. Great. Okay, and so what I'm now going to do is look at the left-hand side of this equation. So n is equal to c to the x, and I'm going to take the log base b of both sides. Okay, so log base b of n is equal to log base b of c to the x, just using that left-hand side equation and taking the log base b of both sides. I'm now going to use the fact that if I have a logarithm where I've raised the number to a power, I can bring the power outside the logarithm. This is a basic property of logarithm, that log base b of c to the x is equal to x times log base b of c. Okay, but now I want to remember the right-hand side of my equation, that x was equal to log base c of n. So this is equal to log base c of n times log base b of c. Okay, and log base b of c is just some constant d. And so what we've derived here is that log base b of n is equal to d times log base c of n. Okay, and that is the definition of big O. Okay, it's in fact equal. In fact, that's the definition of big theta. Great. 2 facts about the logarithm in big O and 1 proof. In this video, we've looked at asymptotic analysis of logarithms, and we've compared logarithms to polynomials. Asymptotically, we see that logarithms grow slower than any polynomial. In the other videos of the lecture, in video 1, we reviewed big O notation, which gives asymptotic upper bounds. In video 2, we looked at variance of big O notation for exact bounds, lower bounds, and strict bounds. That was big theta, big omega, and little o and little omega. And again, in this video 3, we looked at the relationship between big O and logarithms.